Hi, in this lesson we're going to review shear and bending moment diagrams. Okay, let's start with a few definitions. A beam. A beam is a common structural member that carries loading perpendicular to its longitudinal axis. Beams are typically oriented horizontally. A beam loading is known as coplanar parallel force system. We talked about these force systems in Chapter 4. Beams are also known as girders, stringers, floor beams, joists, lintels, spandrels, purlins, or girts. A rotating shaft can also be considered a beam as well. So think about that when you're going to take your machine design class. Okay, these are the types of beam supports and what the reactions are. So this is a roller support. It kind of looks like this in your homework problems. And then the reaction is going to be just a vertical force. Now a pin or a knife edge has both vertical force and a horizontal force. And then if you have a fixed like a cantilever, that has a vertical and a horizontal force and also has a moment there too. So types of loads on beams, you can have concentrated loads or distributed loads, and then the two different types of distributed loads would be uniformly distributed and non-uniformly distributed. So here's our examples of a concentrated load. So here are your two reactions. Here's your load. This is a distributed load. So the distributed load is this W, it's in pounds per foot, or kips per foot, or newtons per meter, and that's how it's designated. And then this would be a non-uniformly distributed load. It's 0 at one end and it increases to a maximum W, and then it comes back down. Now let's talk about the type of beams that we're going to be talking about. This one right here, A, is a simple beam. We have a pin at one end, we have a roller at the other end. Therefore, there's no horizontal forces at all. We have a distributed load, and we have a point load on here too, concentrated load. This is a fixed beam. Okay. Now, if you look at the difference between these two, you can solve for the reactions here of a simple beam using the laws of equilibrium. But for a fixed beam, you can't do that. You have a moment, you have all these loads. So, the fixed beam is a statically indeterminate beam. Here's a cantilevered beam. It's fixed at one end and it's not supported at the other. Again, that's statically determinate. This is a propped beam. It's a cantilevered beam with a prop at the end. That's, again, it's statically indeterminate. And then we have an overhanging beam. That's where loads could be outside of the supports. And then here's a continuous beam. Again, statically indeterminate. It's just continuous. Okay, let's talk about statically determinate versus statically indeterminate. Statically determinate beams, the reaction forces can be calculated using the equilibrium equations, whereas with statically indeterminate beams, you cannot use the equilibrium equations alone to calculate what the reaction forces is. The fixed beams and prop cantilever beams are statically indeterminate. Okay, so I provided you a sheet that calls for what the shear and how to construct a shear and bending moment diagram with guidelines for those. Please refer to that sheet. It looks like this. How to construct a shear diagram: you need to sketch the load diagram, you need to compute the reactions and note these on the load diagrams, and then you draw a horizontal baseline representing the zero shear. And then that baseline should be the same length of the beam directly below the load diagram. I'm going to talk about this in a minute. Then you draw the projection lines vertically downward from the following key points. Every reaction should have a vertical line. Every concentrated load should have a vertical line. in the beginning or the end of a distributed load. Sketch the shear diagram using continuous algebraic summations of the vertical forces, and then locate the points of zero shear. The points of zero shear are going to be the highest moment. Once we start talking about stresses, we'll need to know, because the bending stresses are going to be the highest at those points of zero shear. And then to construct the bending moment diagram, draw a horizontal baseline representing the zero moment directly below the shear diagram. Extend the guidelines used for the shear diagram vertically downward from the moment diagram to the moment diagram, and then calculate the shear areas between the points on the shear diagram. These moments, can be added together for construction of the bending moment diagram. And then plot the moment values. And we're going to talk about how to do all of this. Okay, so that's the guideline for constructing shear and bending moment diagrams. You can find that in your materials folder. Reactions of statically determinate beams are calculated using the laws of equilibrium. External loads on beams are balanced by internal stresses. Okay, so when you're doing this shear and bending moment diagram, you're finding out what the internal loads are, and then ultimately in the next lesson we're going to use those internal loads and moments to calculate what the internal beam stresses are. Okay, so for finding reaction forces, distributed loads are replaced with an equivalent concentrated load. I just got a few cartoons here to show you. These would be examples of how to determine beam reactions. These would be the sample problems. This is your convention for positive versus negative shear. This is your sign convention for bending moments, what a positive bending moment is versus a negative bending moment. And then when you're constructing the diagrams, they're going to ask you to draw bending moment diagrams. And if you have a lot of distributed loads, you're going to have slopes that you're going to have to deal with in your bending moment diagrams. Here was a shear and bending moment diagram of one of the examples in the textbook. As you can see, anytime the shear here crosses zero, that's the point of your maximum moments. So in this case, these would be the areas that you were looking at. Okay, plus 80, this is the area, it's the distance across, this is the 10 feet times the 8 kip shear load gives 80, that's the area. So we increase from 0 up to 80, and then this is negative 80, so it decreases down to 0. And I'm going to end this right here. Please see the example that I posted under the problems.